Hello, welcome to another episode of the IT Wildcard. So, in the comment section of my previous video, somebody asked about encryption, and as you can imagine, and as I think they also mentioned, it's a pretty big area. And so I've had to decide an angle to take with this, because I think, as I mentioned in the video on database sharding, I'm not planning on doing real deep dives. This is going to be helicopter view stuff, unless it's something where it is able to do. I'm able to do a deep dive in fairly short order. So what I thought would be interesting to do in this video is compare and contrast 4 related IT concepts, one of which is encryption, and the other 3, over the years, I've noticed are often, spoken or mentioned alongside encryption. And I thought it would be really interesting to compare and contrast. So that's how I'm going to start this video off. And I'll just talk through each one. Also, I'm just trying out something a bit different, as I always like to add my own twist on this. So there's going to be images that go with this, but I've used Bing Chat to create abstract images about the subjects I'm talking about, and I'm going to see how this might help reinforce the learning. We'll see. Let me know how you find it, whether it does work subliminally in some way. And then I'm going to talk a little bit about, at the end of the video, about how I created these, what I've been working on this week, which is basically more Bing stuff, and then a little bit about some philosophy stuff I've been working on. So yeah, it's going to be an interesting episode, so stick around, and I'll try and make this as interesting as possible and as broad as possible, and also I will include links to articles on the 4 things I'm mainly going to be talking about. So let's start off with encryption, seeing as that's what the original question was about. So encryption is a way of scrambling data so that only authorized persons can understand the information. It's used to protect mainly the privacy and security of sensitive information, and that can be things like messages, passwords, credit card numbers, the usual things that we associate with privacy and security. Now, encryption works very broadly, and remember, with these episodes I'm very much looking at through the lens of modern IT, but bear in mind, I think everything I'm going to talk about today has a historical perspective, either all of it or aspects of it that predate the computer era. So just bear that in mind. But for the purposes of this discussion, think about encryption as working by using a cryptographic key and an encryption algorithm to transform the original data, which you might have heard referred to as plain text, into an unreadable form. And again, you may have heard the term ciphertext used for that unreadable form. Now, the key is a secret value that determines how the data is scrambled and unscrambled, and the algorithm is the set of rules that describe how to perform the encryption and decryption. And once you know that, you might also recognize that those techniques might be possible to be performed without a computer. Now, there are 2 main types of encryption, 2 buckets that it's broadly placed into if you're talking about it. and that's symmetric encryption and asymmetric encryption. So, and it's probably a bit of a giveaway here as to what sort of key you're using. So symmetric encryption uses the same key for both encryption and decryption, and asymmetric encryption uses different keys for encryption and decryption. And what you'll notice is that with asymmetric encryption, specifically, the encryption key is shared publicly, while the decryption key is kept private. And asymmetric encryption is also known as public key encryption. Now, because symmetric encryption uses the same key for both encryption and decryption, of course it's really important that the sender and the receiver are the only people that know the key for symmetric encryption, because it's used for both parts. Symmetric encryption is faster and simpler than asymmetric encryption, but as I've said, because of the problem of, it's only the sender and receiver should know the key, because it's used both ways, it does require a secure way to share the key between the sender and the receiver. Asymmetric encryption doesn't need a secure way to share the key, because you're using the key you use to encrypt is the public key, and you decrypt using the private key. In the article I'm going to share, there'll be an explanation how the public key and the private key are generated and what their relationship is and how that works in overview. But at the moment, just bear in mind that asymmetric encryption does not need a secure way to share the key, but it is slower and more complex than symmetric encryption, as you can probably work out. Asymmetric encryption is often used to establish a secure connection through which you can exchange a symmetrical key, and that is then used to encrypt and decrypt the actual data. So sometimes you can use the two together, and there are systems that do that. Some examples of symmetric encryption algorithms are AES, DES, RC4. Some examples of asymmetric encryption algorithms are RSA, ECC, and I think something called Diffie-Hellman. You'll find encryption crop up all over the place. It's widely used in various applications and technologies such as HTTPS, SSL, TLS, VPNs, emails, messaging apps, cloud storage, etc. Encryption helps prevent unauthorized access, interception, modification or theft of data by a number of different parties, hackers, cyber criminals, even governments, and all other manner of third parties. So that's encryption. And like I said, obviously you can dive really deep into that. It's a massive subject, and there's all sorts of other things to consider, but that's where I really want to stop with that. Now, the next thing I want to move on, which is related to it in some way, is encoding. So encoding is the process of converting data from one form to another for a specific purpose. So you can see where encoding and encryption might be very similar. Now, encoding can be used for various information processing needs, such as data transmission, storage, compression, decompression, application data processing. So I suppose with encoding is that you're more using it where you want to change your information, your text, into a form that is more appropriate for the task in hand, rather than specifically with encryption where you're trying to specifically, stop it being interpreted by or read by third parties you don't want reading it.
So encoding works by using a code and an encoding algorithm to define how to represent the data using symbols, such as letters, numbers, or binary digits. The encoding algorithm is a set of steps that describe how to apply the code to the data. Lots of different types of encoding that depend obviously on the type and the purpose of the data. So some examples are character encoding. So that's where you might take some text data and convert it into a sequence of bytes or bits that can be stored or transmitted by computers. Character encoding uses codes that assign a unique number to each character. So you might hear terms like ASCII, Unicode, UTF-8, those sort of things. Then you get image encoding. So this type of encoding converts image data into a compressed format that reduces the size and improves the quality of the image. Image encoding uses codes that define how to represent colours, shapes, details of the image, etc. And you probably come across terms such as JPEG, PNG, or GIF, however you say that. And you'll notice those often appear as file extensions. Audio and video encoding. So this is a type of encoding that converts audio and video data into a compressed format that reduces the bandwidth and improves the performance of the media. Audio and video encoding uses codes that define how to represent sounds, frames, motions of the media, etc. And again, you might hear format names such as MP3, AAC, H.264. Decoding is the opposite process of encoding, and it converts the encoded data back into its original form using the same code and algorithms. Decoding is necessary for reading, displaying, or playing the encoded data. Now, beyond that, you might also hear the terms lossy or lossless as well, but we're not going to go into those. Again, I'll include links where you can explore the various processes of encoding in more detail. But it is a fascinating area, and I'm sure I've mentioned on other videos, and I'm sure I'll talk a little bit about at the end, my sort of exposure to encoding and what form that normally took. Next up, we have hashing. So hashing is a process of converting data into a fixed length string of letters and numbers called a hash value or a hash. It's used for various purposes, and again, some of this overlaps with some of the other techniques we're going to talk about. But it's used in security, authentication, data integrity, and hashing works by using a hash function and a key to transform the original data into a hash value. And you can see a certain pattern emerging here in the first three things we've spoken about. They all seem to involve some form of key or code in combination with either a function or an algorithm. So in the case of hashing, the key is the input data that can be any type of information such as text, numbers, files, etc. And the hash function is a mathematical algorithm that applies a set of rules to the key to generate a hash value. So here the key is actually the information. It's one and the same. There are different types of hash functions depending on the purpose and the desired properties of the hash value. So some examples are, so you've got cryptographic hash functions. So these are hash functions that are designed to be secure and resistant to attacks. They've got four main properties. So there's a one-wayness properties. So it's hard to find the key from the hash value. So you can't reverse hash values. Because what's called collision resistance, so it's hard to find different keys that produce the same hash value. Pseudo-randomness, so the hash value looks random and unpredictable, and a fixed length.
The hash value has a constant size regardless of the key size. Cryptographic hash functions are used for encryption, digital signatures, password hashing, message authentication, codes, etc. Some examples of cryptographic hash functions are SHA-1, SHA-2, SHA-3, MD5, and so on. Non-cryptographic hash functions, these are ones that aren't designed to be secure and may be vulnerable for attacks. They're faster and simpler than cryptographic hash functions and are used for non-specific purposes, such as data compression, error detection, indexing, etc. And some examples of hash functions are CRC32, murmur hash, FNV1A, and so on. It's got applications in loads of different fields: cybersecurity, data science, database management, blockchain, and it helps prevent unauthorized access, tampering, it's used a lot in actually, or corruption of data by verifying its authenticity and integrity. So really how you apply the hash function is really, and what sort of hash function it is dependent on, are you using it to hash passwords, or are you using it to hash for the purposes of error detection? That's just two main examples. And then the fourth thing I want to talk about is, and I'm going to have problems pronouncing this, you can probably guess what this is. It's called obfuscation. And it's the process of making something obscure, unclear, or unintelligible. It's used for various purposes, such as hiding, protecting, or confusing the meaning of something. And obfuscation works by using different techniques to change the appearance or structure of something without changing its functionality or content. There's many different types of obfuscation depending on the object and the goal of it. So some examples are code obfuscation. So this type converts programming code into a form that is hard to read, understand, or reverse engineer. It uses techniques such as renaming variables and functions, removing comments and white space, adding junk code, encrypting strings, etc. And it's used for protecting intellectual property, trade secrets, or malicious code from analysis or modification. Then there's data obfuscation. So this type of obfuscation modifies the data in a way that preserves the structure and format but alters its value or meaning. So it uses techniques such as masking, anonymizing, encrypting, hashing. So you can see there's a link between this and hashing. Data obfuscation is used for protecting sensitive or personal information from unauthorized access or disclosure. And very simply, that can be even things like, with a document, masking out certain names, I suppose. And as I've said, some of these techniques, if not all of them, or some aspects of them, predate the computer era. Language obfuscation, so alters natural language in a way that makes it difficult to comprehend or communicate. It uses techniques such as jargon, euphemism, circumlocution, ambiguity, etc. Used for avoiding directness, responsibility, or criticism. So it's interesting. So we're getting into areas now that are, not necessarily connected with technology. Obfuscation has applications in a very wide range of fields: cybersecurity, software development, data science, politics, literature. It helps prevent interference, tampering, theft of information or code by making it harder to detect, analyze, or modify. Okay, so let's just go on to Bing, because there's several things here I wanted to talk about, my own experience of the four forms. So probably the first time I came across it was when I became interested as a child in just very simple ciphers. So I asked Bing Chat to actually give examples of 5 early ciphers. I'm going to include these prompts in the description of the video. And one that always seems to come up is this Caesar cipher. So what is the Caesar cipher? So it's one of the simplest and most widely used techniques. And all it is it's a type of substitution cipher in which each letter in plain text is replaced by a letter some fixed number of positions down the alphabet. So you can see the key and the algorithm for doing this are pretty simple, and once you know the key and how that might be applied, in this case you're using the key, which is a number to indicate the shift, if you like, and then you know that that's being applied to the text just purely as a shift, then it's cracked. So you wouldn't be using this necessarily in modern communication systems, although it does give an example here of a complex system for that. Now, one thing that's interesting about substitution ciphers is this other way of cracking them if you don't know necessarily what the shift is. And also once you start to work this out, you can work out what the shift is. And that's what's called frequency analysis. So when you have enough written text, you'll start to notice that certain letters occur more than others, which are used in the language. And so what you can do is you can substitute the letters you think that are the common ones with, the more common letter, and crack it that way, or at least partially crack it till you work out what the shift is. Now, of course, there might be instances here where there's other ways in which this is being shifted, which makes it a little bit more complicated. But if I scroll down, I'll show you the example I got it to show me. So here's how frequency analysis is used. So here's the original, here's the cipher text. And so you can go through and create a frequency table. And then from that, you can work out based on, so there we go, put it in order. And then if you happen to know what the frequencies are normally in English. So you might know, for example, that E is the most common letter in English. So it's likely that E responds to one of the most frequent letters in the ciphertext, such as E, I, or X. Similarly, T and A are also very common in English, so they might correspond to the other high counts here. And so from that, you can sort of work out what the substitutions are. And of course, this does rely on you having a table of frequencies of the most common letters in English, but they can be found all over the place. And I remember as a child, I'm trying to remember the name of the book where I was first exposed to this, but it went through that process. So it taught you how basic substitution ciphers work, and then it taught you about frequency analysis. And there you go, there it is. So that's pretty interesting. So that was probably my first exposure to encryption. In terms of encoding, over the years, I suppose, with encoding, where I've come across it most is taking data that's in one form, like ASCII code, and converting it to something else for the purposes of doing, web queries or certain things, where certain APIs as well, interrogating certain APIs, but also
I've had a lot of questions over the years where people have got a file in a certain format and they need to ingest it into an accounting system. It's a good example, actually. And, they don't really know what encoding it's currently using. And, I've often had to go through with people and, offer up certain suggestions as to what it might be in by looking at it and determining it from that. So I think a lot of what I've done involves that side of things. The other thing, actually, thinking about it, is video encoding. I was at one point dealing a lot with security footage, and you sometimes find these old security systems using these sort of bespoke encoding, or codecs, I think is the correct term, using these codecs. And there are some hacks you can do on the header files to modify. There's often like an identifier string in the header file, and you can sometimes change that to the same, a codec which actually performs the same, just so a system can recognize it, like a sort of playback system can recognize it. And that's quite fun to play around with. Obviously it doesn't always work, but sometimes you find these, what would you call it, like open source codecs, which are actually the same as another one that isn't open source. And by changing the signifier, whatever you want to call it, in the header file of the video, you can actually get it to play back on other things like VLC, like software playback systems. So it's been quite handy over the years learning a little bit about the different containers and the different codecs and how they relate to one another. So that's where I've found that useful. Hashing, I'm just trying to think of specifically where I've come. I mean, I didn't mention it in the context of data sharding, database sharding last week, or the last episode I did. I suppose, obviously, generally, mostly it works in the background all the time. Like, you get any system that saves passwords. You have a hash function performed on the password. I've come across, I suppose, an interesting area between encoding and, I don't know if you'd call it hashing, where document numbers are converted to in a different base. This is probably more encoding, in order to reduce the amount of characters you need to have the document number for sort of where you're working on systems that might still have to use 8.3 file name format. But I think that's more encoding than really hashing. It's using encoding to keep the data length, or the file length name down. So I don't think that's quite the same thing, actually. But I was just trying to think, outside of just what stuff is shrink wrapped into stuff I'm using day to day. I can't think with a specific example where I've had to, I suppose, roll my sleeves up and work with hash functions directly. They're just there in the background on a lot of different systems, and you just almost like take it as a given. Obfuscation is an interesting one. Again, I've heard of examples of people like hiding information in images. Another famous one is where you take some text and it's organized in a certain way. When you line it up, it reveals another message. But again, something I've not used directly. It's more just indirectly working in the background on systems I've used. I don't think...
yeah, again, there's parallel things that don't really count, like, I don't know, taking text, stuff you don't want people to see, and then placing it in a separate file. So I suppose that's a form of obfuscation, but it's not really what I think it's meant in this example. But yeah, it's more like I often think of obfuscation as hiding in plain sight, as another way of thinking about it. And it's not the same as I don't think as being, I don't know if being artfully vague is also the same as an example of obfuscation or not. So yeah, that's just a few examples, or in the case of not where I've sort of come across it day to day over decades. But it is interesting to look out for. Once you know what the 4 different types are, it is quite, it does satisfy your curiosity to think, okay, what container or containers does this thing that I'm doing belong in? And from that, what might be potential risks involved? And is there a better way of doing it for what the use that I'm, putting it to? So yeah. So what have I been working on this week? Well, one thing I've been experimenting in a lot, and I think this is a carryover from other videos I've done, but I'm going to mention it again. So this idea of, using Bing to create images, but in some abstract way, like saying, can you create art that represents something? And I think I've spoken about it and done a post on, can you create art that represents the sound of a certain genre of music? And that's quite interesting to see. But here I did it for this episode to say, can you create some art that represents the concept of, encoding, encryption, hashing? I had a couple of goes at that actually. And obfuscation. So that was quite fun to play around with. And it is interesting to create this sort of abstract art based on a concept rather than a description of what the art should look like. And then the other thing, which I've been using Bing Chat a little bit to help me with, I quite like this idea of being, funnily enough, unclear, probably artfully vague is a better word. I suppose it might be obfuscation, but certainly not trying to make it obscure or unclear. It's really just pushing it a little bit and working out how well it interprets your request in the same way that another human being can take a question and work out what you're saying when the question might be a little bit more vague, because the person answering it doesn't necessarily remember things. So here's a good example. Let me give you an example that might be better. So when you consider the period in philosophy where the schools of thought of rationalism and empiricism are considered to be the most important, with reference to that specific period, what do you see as the key differences between the two schools of thought when considering the subject of human flourishing? So what I was really interested in here was, if you take a period around the time of, I suppose, Descartes, Spinoza, Leibniz, who were the rationalists, and the other side of the equation, which is the empiricists like Locke, Berkeley and Hume, within their philosophy, did they particularly address human flourishing? I could have said it that way, but I chose to say it this way, because at the time I posed the question, I just couldn't remember the philosophers, but I did know there was a group of rationalists and empiricists who were sort of duking it out, if you like. And that also was brought together by Kant. And we're going to just see how it answers this. So does it do that? So says here, let me just read this out. It's pretty short, actually. The period in philosophy where rationalism and empiricism are considered to be the most important is usually called the early modern period, which spans from the 17th to the 18th century. One way to understand the key difference between the two schools when considering the subject of human flourishing is to look at how they answer two related questions. What is the source of human knowledge, and what are the limits of human knowledge? Interesting how it's approached this. So yeah, it's tried to find a way in which, so rather than say, oh, these philosophers addressed it and these didn't, because I know it was addressed by Spinoza. But it's interesting that it's the angle it's taken here. So yeah. So one way to look at how they answer two related questions. What is the source of human knowledge, and what are the limits of human knowledge? Rationalists such as Descartes, Leibniz and Spinoza argue that the ultimate source of human knowledge is reason. They claim that there are some ideas that are innate or present in the mind at birth, such as mathematical concepts or metaphysical principles. They also claim that reason can provide us with a certain and universal knowledge of the external world and of ourselves. Empiricists such as Locke, Berkeley and Hume, did I say Berkeley? I meant Berkeley, if I've said Berkeley before. And Berkeley and Hume argue that the source of human knowledge is experience. They deny that there are any ideas and maintain that all ideas come from either sensation or reflection. They also claim that experience can only provide us with probable and relative knowledge of the external world and of ourselves. When it comes to human flourishing, rationalists and empiricists may have different views in what constitutes the good life for humans. Rationalists may emphasise the role of reason in achieving happiness, virtue and wisdom. They may also value the pursuit of abstract and universal truths as a way of fulfilling our intellectual nature. Empiricists may emphasise the role of experience in achieving happiness, virtue and wisdom. They may also value the pursuit of concrete and particular truths as a way of satisfying our sensory nature. Of course, these are generalisations that may not apply to every rationalist or empiricist philosopher. There may be some points of agreement or overlap between the two schools, as well as some variations or nuances within each school. For example, Locke acknowledged that reason plays an important role in some knowledge, such as moral truths. Hume argued that reason alone cannot motivate us to act, and that we need passions and sentiments to guide our moral judgments. I hope this helps you understand the main differences between rationalism and empiricism in relation to human flourishing. So, I was vague, it was vague, no surprise there. But what I could probably then do is, how can I best word this so it isn't equally vague? Can you indicate which of these philosophers had something specific to say about flourishing? Now, I'm hoping that it might pick up on the fact that Spinoza's ethics does actually deal ultimately with human flourishing through, I believe, working rationally through cause and effect and seeing how causality affects us and our passions. So we'll see. It's definitely having to really think about that. Oh, so yeah, it's not, this is something I've noticed before, did I? Yep, no. So sometimes it forgets, selectively forgets what you were talking about here, even though I said which of these philosophers. and I don't know why this is doing this a lot more now. It always seemed a lot better at locking into the discussion thread. So we started off talking about encryption, and we're now into 17th, 18th century philosophy, rationalist empiricists. But, you know, part of the idea of doing this is also to talk about what I've been working on this week and how I've been leveraging, where it isn't IT, you know, how I've been leveraging specifically Bing Chat. Okay, there we go. We're getting there. It doesn't want to talk about, so let me just see if I'm going to have to force it on. I should have been more direct. I shouldn't be so obscure. What about Spinoza on this subject? Again, sometimes you have to spend a little bit more time going, yeah, no, I still want to talk about this. I don't want to talk about how to make a really nice second breakfast or anything like that. Yep, it's picked it up. You've got to corral it back in. There we go. Argues that human process is meant to have adequate knowledge of ourselves and the world. It enables us to form adequate ideas and act upon reason. Immanent ethics, which bases its normative claims on how things affect one another's cognitive flourishing. Excellent. So I think I'm going to stop the video there before I go further down various rabbit holes and somehow manage to cunningly combine both encryption and Spinoza in some way. Thanks once again for watching. Bye for now, and I will catch you in the next episode.